Very good morning, everyone. So, welcome back to the class. And today we are going to talk about a very interesting topic, a very interested, discussed question during the interviews related to something called as master theorem. Yes, we have already discussed earlier that whenever we have a recurrence relation and corresponding to recurrence relations time complexity to be found, then time complexity finding directly and fastly, we have got third method, which we call as a master theorem method. So today we are going to see, we have already discussed the substitution method, and we have also discussed the recursion tree method. These were the first and second method. And today we are going to see about the corresponding master theorem. Well, it's a direct method. It's a direct process available, or we normally say it as a cookbook method, through which you can directly find out the time complexity without going for any extension, expansion, tree-mation, any rigorous calculations. No, direct solution available based on certain rules, based on some rules or some cases. So this is an excellent method and fast method. So this is what we are going to see today now. Well, another good thing about this is using master theorem, we will be able to get theta notations time complexity, exact time complexity we will be able to estimate, not just lower or upper bound. So with help of a recurrence tree, normally we targeted to have, say, upper bound to be calculated using a recursion tree, or substitution method also we have ultimately targeted mostly upper bound, because one side less than equal to etc. can become easy. So mostly we were doing this earlier. Earlier we were targeting mostly on upper bound, but using so connection was reset. I have just again connected. So we said that earlier we were mostly targeting the upper bound, but using master theorem, we will be able to get the exact bound, and that will be another advantage. And that also fast calculations, direct calculations, no tree, etc. needed. How to do that? Let's go one by one. So this theorem is mostly used, as in other cases we said, that to solve a problem of recursive in nature, effectively in this, there will be always, this is a contribution coming from either the divide nature or the corresponding combined nature, or I'll say not oblique, I will say divide plus combine, because both steps are going to be non-recursive. So this Fn is effectively contribution of a divide and this. So it will be some asymptotic value, or some asymptotic value, or in terms of n, it will be some function of n. So this will be a calculations coming from that side. And this vector tells A has to be greater than equal to 1, because minimum one recursive call must come. And we say B has to be greater than 1, that size must reduce. So obviously must reduce means equality cannot be acceptable, must be reducing in every recursive call. So if I say that these conditions are okay, so this effectively means that the problem is being solved recursively. So calling recursively A times, calling recursive function, or calling recursively, I say normally A times, that is required, and calling with size, reduced size. Obviously call must come with reduced size, say n by b each. So A calls with n by b size. Of course, if all of them have not the same size, then we probably use recursion tree, etc. But for solving using master theorem, this will be solved. So if I have got Tn to be Atn by B plus Fn, then master theorem can be used. Of course, some conditions will apply, but applicable. If I have Tn as Atn by B plus Fn. And then I will say, effectively, it is going to identify, loosely speaking, I will say, it will check whether children will contribute more in the recursion tree, like we have seen the children. So children meant effectively recursive calls. Whether children will contribute more or both will contribute equally. Both equally means children as well as root. That means we are saying recursive calls and we are saying non-recursive contribution. Or whether root contributes more. Root contributes more effectively means that Fn is at the root available. So that means whether Fn contributes more or not. So this is effectively, loosely speaking, and we always know that dominating term decides the complexity. Dominating term decides the complexity. So accordingly, we will be deciding the total complexity. For example, I will say case 1 will mean effectively that children, or I say recursive calls, children effectively means recursive calls, they contribute more. Effectively meaning that Atn by B will contribute more. So this will decide. So we just say that this will be the deciding term as it will be the dominating term. So case 1 will be corresponding to this situation. Similarly, I will say case 2 will mean both equal. So there will be a separate way of calculating. And case 3 will mean that root contributes more. Root effectively means that is my Fn is more contributing. So I will say more contributing or more dominating. Then accordingly, this will decide. So Fn will decide the time complexity. That is effectively, loosely speaking, the corresponding master theorem. Now we will go mathematically as per exact definitions, and accordingly we will formally define and calculate the different time complexities. So in all these cases, theta of something will come. In case 1 also we will get a theta of something. This case will also give theta of something. This case will also give theta of something. So that is it. Going further, now let's formally define definition. So I say, if I am talking of A, T, N by B, so I say let A be greater than equal to 1, B be greater than 1, and we have T of n time complexity calculated through recursive definition as this. Then we say first case. I say, normally I will say E, T, N by B is mathematically it will be found that it will be contributing something like n power log BA. From recursion tree you can verify later, but yes, this I say normally because of this term, contribution is going to be in terms of this. So first case will be if my Fn is less dominating. So that will mean I will say if my Fn is big O of n power log BA minus epsilon, where epsilon has to be greater than 0, some positive value. This effectively means that A TNB by B is going to contribute the n log BA complexity, but Fn has value less than this, and I said upper bound. So I am saying that in any situation, it is guaranteed that Fn will be never going to be more than n log BA minus epsilon, meaning that effectively means that Fn is less dominating, or Fn is less contributing than n power log BA. So if that is the case, then I will say my total time complexity will be theta of n power log BA, because this term contributes in these terminology, and this is the dominating term. Of course, I will say some conditions apply. So I will define what are the rules, what are the conditions. Then comes case 2. Case 2 says if Fn is also equal to, that means it is equal to will mean exact bound by n power log BA, then both are equal, both contribute, and both contribute will mean that my time complexity will be said to be n power log BA into log of n. Effectively meaning, here I am using the theta notation. I am saying that Fn is exactly. So again, because of a connection, I had some disturbance. So Fn, I will say, is exactly bound by n log BA. So my recursive term also contributes n power log BA, and this also contributes something similar or exactly equivalent to n log BA. Then my time complexity is claimed to be this one. It is going to be n log BA into log n. And then comes case 3. So case 3 effectively says, other case, that is if Fn is going to be contributing more than n log BA, that means this I am using to have omega notation, n bar log BA plus epsilon, and this is a lower bound. So I am ensuring that Fn is going to be more contributory in all cases, because minimum is this log BA plus epsilon. So epsilon must exist. That will mean epsilon must be greater than 0. So guaranteedly, I am ensuring that Fn contributes more than n log BA, more contributing than n power log BA. So omega notation is taken, plus epsilon is already there. But if I write here big O, that would mean upper bound. Upper bound means contribution can be lesser than that also. But if I say lower bound, so it means a minimum this much contribution is guaranteed. If this contribution is guaranteed, then I say the answer will be based on Fn. So my time complexity will be based on this Fn, and that will be, of course, said to be theta of Fn. So loosely speaking, but here I will say again a condition apply. So condition for star 1 and star 2 I will define later, but I quickly write once again all three cases, that if I have master theorem applicability, then for A, T n by B plus Fn, if I am saying a T of n to be computed, then I say case 1 with a certain condition. I will define now the conditions also, that if Fn is going to be upper bound by n power log BA minus epsilon, epsilon is greater than 0, then I say the time complexity will be theta of n bar log VA. Case 2, it says that if Fn is also equal to exactly n power log BA, no epsilon existing at all, then my time complexity will be theta of n power log BA into log n. And then I say case 3, with case 3 means Fn is lower bound, or Fn is going to contribute more than n power log BA. That means there some epsilon guaranteedly exists. Then my time complexity will be equal to theta of Fn itself. So this, but here I said some condition apply. Here I said some condition apply. Condition we will understand later. And these are the 3 rules. So what are the conditions? Now we go for the condition. I say in this case, the condition will be that Fn is polynomially smaller than n log VA. What does polynomially smaller mean? Mathematically, you might have some idea. Otherwise, I'll explain. And in case 3, the star condition means Fn must be polynomially larger than n log VA. So you can easily see that polynomially larger will ensure that this contributes more. But this has another condition also, which is said to be a regularity. The second condition which we are talking is that regularity condition must hold true. What is that regularity condition? It simply ensures that the root, that is Fn, does more work than its children, as we are expecting as per this condition also. So regularity condition must hold true, must be true. And what is that regularity condition? It simply says a f of n by b is less than equal to c of Fn for some constant c to be less than 1 or less than equal to 1. Remember, here I'm talking that if the children were also being considered for the same function or same contribution using n by b size a times, then I say in that case I should be able to ensure that my root with some constant can be considered to do contribution more than or equal to at least as good as the children's contribution. This will be mostly true for our algorithmic programming. Mathematically, this can be sometimes false when my Fn has, say, sine function or cos function, etc. So mathematically, that gets violated. But programming wise, most of the time this will be true. So for the time being, we assume that this condition will be mostly true, as we are already saying that this is minimum. Fn is minimum, or a lower side it is n log BA plus epsilon. So roots contribution we are expecting to be higher. Here this is mathematically verified that instead of a t n by b, if I consider the same functionality for n by b on the children side, still the corresponding contribution of Fn is bigger. So without bothering much about this, we can continue and say that let's assume this to be true and understand that for condition 1 or case 1, polynomially smaller must be true, and for condition 3, case 3, polynomially larger must be true, and regularity condition will be mostly true in programming environments. So let's go one by one. I take first case. Let's assume Tn is equal to, I'm taking the same example as taken in the book also. So it is equal to 9Tn by 3 plus n. First aim will be always calculate n power log BA. So in this case, this is B. So I say B is 3, A is 9. A has to be greater than equal to 1. B has to be greater than 1. And Fn is in this case n. So I'm going to see which case applicable. N power log BA means n power log 3, 9 effectively becomes n power square. So I can easily say this is n square. I can guaranteedly write Fn as n raised to 2 minus 1. Means that epsilon exists because I wanted Fn to be written as Fn must be satisfying n power log BA plus minus epsilon. In this case, epsilon exists. So case 1 applicable. And I assume it is polynomially smaller. So what is that? We will see. But assuming this is true, I can easily see my time complexity will be said to be theta of n log BA. Log BA I have calculated already, and this becomes theta of n square. So that will be the first situation where I can guaranteedly claim that this is going to be my answer. Then going another case, second situation, where I say, let's assume Tn is given to be equal to 3t, or I'll say, let's take the same example given in the book, Tn equal to 2n by 3 plus 1. Some mathematical relation where recursive call is called with a 2 by 3. So A is equal to 1, B is 2 by 3, or so B is effectively 3 by 2 because I have said 2 by 3 is in the numerator. So if I say n by B means B will be 3 by 2, and Fn is guaranteedly 1. Calculate n power log BA, n power log 3 by 2 of 1. I can easily say 1 means n power log of 3 by 2, and I can say this is going to be 3 by 2 power 0. So I can easily say this will become effectively n power 0. That becomes 1. Because 1 can be always represented as a 3 by 2 power 0 or any x power 0 as 1. So I can easily see in this case, this contribution is 1. Fn is also 1. Fn is exactly equal to 1. That is n power log BA. So both have equal contribution. So I will say my time complexity will be theta of n power log BA into log n. N power log BA we have calculated as n power 0 into log n. So effectively I can say this is going to be equivalently claimed as theta of log n. Then going to third case, case 3 when it will be applicable. So I say if I assume Tn equal to 3Tn by 4 plus n log n. In this case, A equal to 3, B equal to 4, Fn is n log n. And in this case, if I calculate n power log BA, that will be n power log 4, 3. If I know exact value, this is equivalent to saying it is 0.793, approximately 0.8. N power log 4 and 3 is less than 4, so value is less than 1. Now, what is my Fn? Fn is given as n power n into log n. I can guaranteedly say n power 1. And if there is any power because of log n which I can claim, even if not, but I can guaranteedly say that Fn has minimum epsilon available in the positive value. I can write that Fn equal to in minimum this is going to be greater than or equal to n power 0.79381 plus, let's say, 0.207, because this total becomes 1 and my Fn is guaranteedly n power 1, maybe plus minus something, but this power is guaranteedly true. So I can guaranteedly claim that this is true. If true, it means case 3 applicable, because this value is n power log BA. N power log BA is going to be, or I'll say not n power, I'll say this is nothing but log BA's value. So Fn is log BA plus something. So I can claim that in this case, case 3 is applicable directly, and I can guaranteedly claim based on this that the corresponding time complexity will be based on Fm. So my time complexity will be theta of Fn. Theta of Fn means Fn given to me is n log n. So I can say it will be claimed to be theta of n log n. In this case, the point worth remembering is that log n could be something as giving n power something. So I can say n power 1 was a minimum guaranteed, but this I can equivalently claim if log n is some n power epsilon or some n power delta, say this I claim. So I could say if it was n power delta, then I could say it will be n power 1 plus delta. But whether it log n can be claimed to be n power delta or not, this is a question mark. And this is how my star 1 and star 2 conditions come into picture to be discussed now. So when I said polynomially smaller or larger, that is now we are going to see. Regularity condition, as I already said, that mostly applicable. So let's now understand what do we mean by polynomially smaller or larger requirement. Let's take another case. Say I say Tn is equal to, I'm going to take case of a T2Tn by 2 plus n log n. And through this example, we will understand everything. A equal to 2, B equal to 2, Fn is n log n. So Fn is n log n. So if I say here now, I can say n power log BA will be n power log 2 of 2. That becomes n power 1. Now, so my one side is this, because of recursive parts. Recursive parts will give this much contribution, that's for sure. Fn is n log n. So I have to find out, is Fn polynomially or is Fn polynomially larger, because equality is guaranteed, or not? If yes, only then case 3 will be applicable. Because case 1 is not applicable, power is n power 1, Fn is guaranteed n power 1 or more than that. Then equality Fn is not only n power 1, it has got along with this log n. So my Fn is n power of 1, and I don't know whether plus something is possible or not. This is what I want to see by comparing. So then case 3 can be used. So now I say, if I can write, or I will clearly say, if I can claim that Fn is exactly or greater than equal to some n power 1 plus epsilon, where epsilon is guaranteedly greater than 0, then I will be able to do that. That will mean that, can I claim that log n is equivalent to some n power delta or n power epsilon? And this is what polynomially larger means. It means that if I am talking of log n log n can be considered to be this, provided I can guaranteedly have some epsilon. But this is actually mathematically not possible. I am not guaranteedly able to claim any fixed value of epsilon which guarantees that log n will be growing. So polynomial larger will mean that log n must grow greater than some n power epsilon, must grow. I say Fn must grow larger than some n power epsilon. So I once again say, what does polynomially larger mean? It means Fn divided by n power log Ba must be a polynomial. Must be a polynomial. That's why it is called as a polynomial larger. So polynomially smaller will mean Fn divided by n power log Ba. This ratio, if I'll say this ratio must be polynomial. If it is a polynomial, I will say must, let me correct that, write clearly, must be a polynomial. It will become polynomially larger. And obviously, if I say reverse, that n power log Ba divide by Fn, if it is equivalent to a polynomial, then I will say, then Fn will be polynomially smaller. Polynomially smaller. So we have to prove that. Proving that will effectively mean, for example, this case. This case, I am seeing that yes, Fn is going to be n log n. N log Ba is effectively n power 1. So I can guaranteedly say this becomes log n. If it is a polynomial, then it is polynomially larger. Then I can say Fn is polynomially larger. So if I am not able to get that, it will not be. Mathematically, you all probably know. If you don't know, maybe you can revise your mathematics. Log n cannot be represented as some n power epsilon, not a polynomial. Not a polynomial will mean case 3 not applicable. Case 1, 2 obviously not possible in this case. Hence, I will say master theorem can't be used, not applicable. So this is what effectively the rules of star 1 and star 3 mean. Similarly, for star 1, we will ensure the similar scenario for the case 1 also. So this is exactly master theorem. Now I'll be winding up and my connection is very unstable. So I'll say that I'm giving you some homework to try, and you must try question 4.5-1, 4.5-3 on page 92 and 93 of Theorem 3rd edition, which are given certain questions, problems to be solved. Plus, I will say, also read 4-5 on page 109 of Theorem 3rd edition. So, 3rd edition. This is a problem given as a chip testing problem, when a very interesting problem. So you will understand how algorithms can be used in real life situation for doing efficient solutions. So it's a chip testing problem. Read that and think of possible solutions to this, and then discuss within your friends also, and maybe in the class also we will discuss sometimes if the time permits. So do this, and then I will say also for your practice, for your knowledge, that there is a concept of extended master theorem, so that the cases when normal master theorem was not applicable, as we have already said that in case 1 also polynomially smaller was needed, case 3 polynomially larger, as well as regularity theorem was needed. So extended master theorem given in many platforms, you can read from there. It will be useful in gate-like questions or a faster solutions for situations where you have non-applicability of the master theorem. So you can read this also, at least for your knowledge and for your faster solutions, for your knowledge and